Okay, I think we're ready. Okay, thank you everyone for coming. Our speaker today is Dr. Dan Fu, Assistant Professor in the Department of Atmospheric Sciences at Texas A&M University. Dr. Fu earned his PhD from Texas A&M in 2018 and his bachelor's from Ocean University of China in 2013. His research sits at the interface of weather and climate, focusing on how climate variability and climate shape the predictability of extreme events like tropical cyclones, atmospheric rivers, heat waves, and droughts. He uses high-resolution weather and climate simulations, including WRF, MPAS, and CESM, alongside machine learning approaches to uncover the physical drivers behind these events. His recent work has appeared in Nature Geoscience and Nature Communications, and he currently serves on the editorial boards of IOP Machine Learning, Earth and Nature Communications, Earth and Environment. Sorry, I'm messing that one up. Nature Communications, Earth and Environment, as well as associate editor at the Journal of Climate. He is also a member of the CGD advisory panel. Please join me in welcoming Dr. Dan Fu.
Thank you very much, John. Okay, yeah. Thanks, John, for introduction, and thanks very much for having me. So before I start, I would like to especially acknowledge the support from the NCAR's Faculty Fellow Program. So actually, I haven't been here for several times before, but it's actually my first time to stay here for an extended period of time, which is roughly half of my summer vacations, and I can do some continuous work here. So I really enjoy these experiences and appreciate this opportunity. So today I'd like to present some of our recent results that demonstrate how to use the higher resolution Earth system model simulations to improve our physical understanding and the prediction skills about extreme weather events. So the results I'm going to show is a part of the MESACLIP project, which is a collaboration between Texas A&M University and the NCAR CGD lab. So here shows our project logo. I think many of you may have already heard or seen our logo before, and I hope by the end of my presentations, it can deliver you a more holistic insights about what we have been working on. So here's the outline of my presentations. So I will start with some brief introductions about MESACLIP and accompanied the large swathes of the high resolution simulation ensemble using the Community Earth System Model, CISL. So although MESACLIP has already demonstrated some very significant improvements in the climate science, including the mean states, the trends, and the variabilities, so what I am focusing on today is from the aspects of the extreme weathers as well as some AI application. So specifically, I will talk about how we use the high resolution model to improve our physical understanding of the extreme precipitation simulations, as well as to constrain the future projections uncertainties. I will also talk about how we leverage these system ensembles for the risk assessment about tropical cyclones-induced compound wind and the rainfall hazard. And lastly, I will show you some ongoing efforts that using the MESACLIP data sets for the machine learning purpose, including the tropical cyclone season predictions, and also some purely data-driven AI emulator for the Earth system simulation. All right, so MESACLIP in a nutshell. And MESACLIP stands for the understanding the role of the mesoscale atmosphere-ocean interactions in the seasonal to decadal climate prediction. And this is a collaboration between the Texas A&M and the NCAR CGD. On the NCAR side, the Goken and the Fred are the lead, and on the Texas A&M side, Ping Qian and myself are the PIs. So the scope of our research is try to understand if by considering the mesoscale atmosphere-ocean interactions, whether it will provide some additional predictable component in the Earth system. And beside that, we also want to know if the higher resolution climate simulations can shed some new light on our physical understanding of the climate changes, especially the extreme events as well as extreme events predictability. So in order to do that, we have conducted a large swathe of the simulation using the high resolution CESM version 1.3. So here, the high resolution I mean is roughly 25 kilometer resolution for the atmosphere and the land, and roughly 10 kilometer resolution for the ocean and the sea ice. At this resolution, the CAM is capable to partially resolve the tropical cyclones. So in our field, we typically call this as tropical cyclone permitting resolutions. And also, at the ocean side, it can resolve many aspects of the mesoscale eddies, not fully resolve mesoscale eddies, Peter is here, but it still can resolve many aspects of the mesoscale ocean features. And here shows a table that lists all the experiments that have been working on and has been finished. So essentially, we have finished a 500 years of a pre-industrial control simulation with a perpetual 1850 climate forcings. And accompanied with that, we have historical and transient climate simulations with a Timberman ensemble size spanning from 1920 to 2100. We have run a different scenario, like RCP 2.6, 4.5, 6.0, and 8.5. So far, we have finished the Timberman ensemble for 8.5 and 6.0, and still increasing ensemble size for 4.5 and 2.6. And we also made some sensitivity tests to analyze the climate sensitivity as well as the role of the stratosphere ozones and also Atlantic fresh waters impact on the climate system. And this simulation has been still working on. Besides these transient simulations, another very important contribution of our projects to the prediction community is through the decadal prediction initialized ensemble. So in this setup of the experiment, we initialize the CESM twice a year, either on the May 1st or November 1st from the 1980 to the 2023. For each of the prediction, it lasts for the roughly 5 years with Timberman ensemble. So this is actually a very extensive amount of simulation. Collected together, this decadal prediction experiment actually contributes more than 400 years of the simulation already. Besides this high resolution simulation, we also try to repeat the simulation with a corresponding low resolution SE dicore CESM. And many of the simulation has been done, and part of the data are available through the CISL GDEX platform. And for the rest of the data sets is also available on the GLADE system. So here shows an animation that movie that I made using the MetaClip data outputs. From the gray color scale, you can find the brightness temperatures of the cloud top, and also the rainfall is showing in this rainfall color scale. This is not just an eye candy, but actually it tells us that at 25 kilometer atmosphere resolution, it can start to simulate some intense rainfall storm, especially not only just in the mid-latitude, but also in the deep tropics. So as I will show in more detailed way, this movie actually convinces us that we can use the 25 kilometer CSMHR to bridge the extreme weather sciences and climate sciences. All right, let's move on to scientific discovery and talking about the extreme precipitation. So when we talk about extreme precipitation, future changes, the Clausius-Kaplan relationship has been a long golden standard. And it tells us that extreme precipitation is likely to increase by roughly 7% per degree Kelvin of warming, and it's actually provide us a first order thermodynamic constraints for the future extreme precipitations. However, the recent study tries to emphasize the importance of the dynamical factor, not just from the thermodynamic moisture alone. So here, the top panel figure shows the projected future change of extreme precipitation using CSM1 large ensemble. The bottom is a similar plot, but based on simplified multimodal ensemble mean. The left column figure shows the projected extreme precipitation changes as solely considering the thermodynamic changes, while the right column figure shows the results by considering the dynamical changes, which is due to the local dry air convergence. So consistent with our understanding of the Clausius-Kaplan, the thermodynamic contribution is pretty homogeneous over the globe, but in terms of the dynamical contribution, it is actually heterogeneous. You will find that the dynamical impact over the deep tropics is non-trivial and actually as probably most important by the thermodynamic contribution. While the contribution from dynamics impact to the mid-latitudes are more mixed, so you will find some positive influence in the Asia, but some negative influences over the central US. One big caveat of this type of analysis is that they are heavily depend on the cost of solution of the global climate simulations. and in which we know that the model is filled to capture this very intense precipitations as well as the deep convection. So this partitioning may heavily depend on the choice of the cumulus parameterizations, in which is a big component to determine the convection strength in the low resolution simulation. So to constrain this uncertainty, of course, the most precise way is to run a global storm resolving simulation for a long time and do a very rigorous moisture analysis budget analysis. However, this may not be feasible because of the huge demands of this global storm resolve simulations computational cost. So considering this knowledge gap, we try to ask ourselves whether using our 25-kilometer CSM high resolution model can shed some new light on this knowledge gap. We acknowledge that although 25-kilometer resolution simulation still depends on the cumulus convection parameterization, but compared to the standard 100-kilometer, it can potentially be more precise in capturing the deep convection. So more importantly, we want to see by doing some analysis on our existing data sets, can we lead to some new physical understanding? Of course, the step one is to make sure that our 25-kilometer simulation indeed improves the extreme precipitation simulation comparing the standard 100-kilometer resolution of the CSM. So in order to do that, we made some quite comprehensive comparisons using the iMERGE datasets. So here shows the 99th percentile of the extreme precipitations from a different data source. Panel A shows the satellite observation from iMERGE version 7, and panel B shows our Timberland ensemble of the MesoClip high resolution data simulation data. And panel C shows the low resolution simulations. And you can see that for the low resolution model, it underestimates extreme precipitation quite significantly. For example, over the southeast of the US, where we sometimes experience more than 100 millimeter per day of extreme precipitations, this is quite low in the low resolution model, which can only reach to roughly 50 millimeter per day. And this deficit is actually pretty nice improved in the high resolution simulation. As you can see, some hotspots in the southeast of the US, as well as in the South America, and also some improved intense extreme precipitation in the East Asia. And of course, we do see some offsets, some degradations in the Africa region, especially over the Africa low-level JS region. But overall, we are very pleased to find that the high resolution simulation indeed shows a very promising improvement. And what is even better is that we do see a systematic improvement, not only just confined to the CSM high-res, but to a general body of the high resolution simulation. Here, the panel D shows the results from the high resolution SMIP6 high resolution high-res MIP protocol, and the panel E shows the standard resolution from a SMIP6 simulation. So upon combining the different modeling center results, actually we find the panel D resemble the panel A the best. So we do see the improved simulation, extreme simulations by increasing the resolution from roughly 100 kilometer to 25 kilometer. We next try to understand if this improvement is physically plausible. We don't expect this good result due to the wrong reason, right? So to do that, we can try to make some more process level understanding. So in the modeling world, we can actually partition in the total precipitation to those coming from the resolved scale precipitation, which is directly output by the cloud microphysics schemes, plus those precipitations come from the subgrid scale parameterized rainfall, which is due to the shallow and deep convection parameterization. So in the panel A, here shows the extreme precipitation differences between the high-res and the low-res, while the panel B shows corresponding differences in the resolved scale microphysics-induced precipitations, and panel C shows the subgrid scale precipitations from the cumulus scheme. And which actually very shocked us is that the overall differences between extreme precipitation seems to be solely come from the resolved scale processes, while the subgrid scale process actually tends to offset this enhancement. So this result suggests that the stronger precipitation in the high resolution model is not due to the overreactions in the cumulus parameterization, but is due to some resolved storm scale processes. So we further try to decompose these storm scale processes into to the dynamical contribution, which is caused by the dry flow convergence of the flow convergence of the dry air versus the thermodynamical contribution, which is due to the column of the humidity. So the bottom panel figure shows the results of these decompositions, and we further find that this enhanced moisture flux convergence, which is proportional to the extreme precipitations, is driven by this enhanced dynamical impact, which is through this dry air convergence induced the upward motions. While the column humidity between the higher res and lower resolution model seems to be quite similar. You will see the differences is pretty much the minimal. This result further confirms that it is really the resolved scale, the dry convergence that leads to the strong precipitation in the high resolution model, and this is due to a physically plausible explanation. So besides this Eulerian-based moisture budget analysis, we also deploy a Lagrangian-based feature tracking analysis to try to see if the high resolution model can indeed simulate the convective system better comparing to lower resolution counterparts. To do that, we apply the multi-object analysis of atmospheric phenomenon package, which is short as a MOAP. In this package, we can try to track the 12 different atmosphere features using roughly 15 atmosphere variables. And the top panel figure shows the scale diagram of the different atmosphere features, including the mid-level and surface cyclones, anticyclones, mesoscale convex system, atmosphere rivers, as well as jets, as well as some equatorial waves. The x-axis shows the horizontal scales of different features, while the y-axis shows the temporal scale. The bottom box plot further elaborates the scale diagram in terms of the PDF distribution. So, consistent with our expectation for the synaptic scales storm system, the high res and low res both show some good consistency with observation. But the most striking differences is actually over the MCSS regime. So if we look at the black, which is showing the observation, and the red, which is high-res simulation, they all suggest that the MCSS should have the average size of roughly 200 to 400 kilometer diameter. But for the low resolution model, it falsely actually suggests MCSS has a size of roughly 1,000 kilometers. This is well beyond the meso alpha scale, and this is not physically reasonable results. Besides on the scale, it also suggests that the low resolution model may have some big biases in the CSM frequencies. Here's the top panel figure shows the MCS's frequencies from the observation on the left, and the high res in the middle, and the low res in the right. I want to note that in order to show up some color, I have to artificially decrease the color bar scale by a factor of the 50. But even with that, the low resolution model in the majority parts of the globe shows the white color, suggests that they are actually filled to capture MCSs at all. On the other hand, the high resolution model can capture this spatial pattern quite reasonably. We can see a MCS's prevailing regions in the southeast of the US as well as in the South America. But we still see some biases in the Central Africa, which deserves some future analysis. But overall, we find this MCS simulation is pretty much very significantly improved compared to a lower resolution model. And the bottom final figure further try to highlight those atmospheric phenomena that's corresponding to the extreme precipitation events. So different color indicates different weather type. And you can see from the observation and the high resolution model. So over the mid-latitudes, it is essentially the extreme precipitation is driven by the MCSs, which is showing the red color. On the other hand, for the lower resolution simulation, you will see that there's no red color at all. So the mid-latitudes extreme precipitation events are driven by the fronts or driven by the jet system, which is clearly not correct. And we find this high resolution model indeed captures this relationship quite reasonably good. And Before we make this analysis, to be honest, we don't expect 25 kilometer resolution can able to depict the MCSs. But this result is pretty shock. We also want to make sure the detected MCSs is really the MCSs in our mind, right? So that we made some more careful evaluations over the CONUS regions where we have more advanced and consistent observation network, as well as some higher resolution regional simulations. Here shows you a morphology of the MCSs in terms of the precipitation field, and this is a composite of the precipitation with following the tracked MCSs. The panel A shows the satellite observations, and the B is a NOAA-based in-situ observation network, and the C is a 4-kilometer regional WRF simulation results, and the panel D is our global 25-kilometer CSM high-res, and the panel E is a EI5. So I'm not going to say EI5 is the observation, but since EI5 has a comparable resolution as a CSM HR, so I also put it here as a references here. The top panel composite is made on the common quarter degree resolutions. I interpret every different data set resolution to the common quarter degree and then make a composite. For the bottom left, which is highlighted in this green box, it is showing the composite made on the raw resolution. For the iMerge, it is 1/10 degree, 10 kilometer. For the snow observation, it's roughly 800 meter. And for the WRF, it's a 4 kilometer. And also within this red box, I try to estimate contribution due to the subgrid scale prime price rainfall. So for the CSM-HR and the EI5, I plotted here. So this result is actually very interesting. It suggests that even within 9 to 25, which means 3 by 3 or 5 by 5 grid point, so our 25 kilometer resolution is capable to resolve these deep convections. And this the rainfall's amount is actually pretty consistent with the 4 kilometer WRF simulations. And more interestingly, this extreme precipitation is largely driven by the resolve scales because this subgrid scale rainfall is very weak. So the color bar here is just like 1/5 of this color bar showing in the composite. This suggests that it is really the resolve scale convections leads to this improved MCSs simulations in our CSM's high-res setup. All right, so let's talk about the future changes. And here shows the projected future changes using the end of century, my historical period. The top panel figure shows the high resolution simulation. The bottom figure is the low resolution simulation. The black box suggests a total changes, and the red box highlights the changes due to dynamical factor, and this blue box indicates the changes due to the thermodynamics factor. So after the global average, we see that the high resolution model can lead to roughly 41% of the increase in the extreme precipitation, while this increase is roughly 25% in the low resolution counterparts. And most strikingly, the thermodynamic contribution looks pretty much the same between the high res and the low res. In terms of global average, you will see the two numbers are almost identical. For the spatial pattern, although it's pretty much similar. But the biggest difference is in the dynamical contribution. You'll see that dynamical contribution leads to roughly 25.8% of the increase in the high resolution, but only leads to roughly 8.9% of the increase in the lower resolution counterparts. So combining this thermodynamic and dynamic all together, it suggests that it is really the dynamical components leads to the stronger extreme precipitation future changes in the high resolution model. While this process is actually largely biased in the lower resolution model. So, which means that even if we combine all the existing CMIP6, CMIP5 type of the lower resolution simulation, our projected future changes of extreme precipitation is very likely to be underestimated. In order to have more precise future exchange precipitation projections, we may need to consider in the impact due to the dynamical factor. So here shows a section summary, and throughout our analysis on the extreme precipitation, we find that although at 25 kilometer resolution, the CSM-HR cannot explicitly resolve the clouds and deep convection, but still remarkably outperform the lower resolution counterparts in the extreme precipitation simulations, simply because it's a better representation of the storm scale local convergence. And more interestingly, the 25 kilometer CISL seems to be captured the mesoscale convex system to some extent, which maybe can be used as a useful tool to understand the MCS's variability as well. In the context of the future changes, the thermodynamic contributions are pretty much similar in between the high-res and low-resolution model, but the dynamical factor is roughly 3 times stronger in the high-res compared to the low-res. So as a result, extreme precipitation future changes is much stronger in the high resolution comparing to the low resolution counterparts. So maybe I can move forward and I will do the Q&A afterwards, okay? So now let's talk about the tropical cyclone. As I briefly introduced that the tropical 25 kilometer resolution, the model is capable to partially resolve the tropical cyclone dynamics. So it is actually sitting a sweet spot to considering both the tropical cyclones frequencies as well as tropical cyclones intensities. So here shows a comparisons of what we actually observed, the tropical cyclones tracks as well as the intensities, and also the simulations in our mesoclip data sets. You will see that our model simulation tends to overestimate the tropical cyclone frequency to some extent. On average, we have 104 tropical cyclones TCs annually, but in reality, it should have roughly have 82 to 83 tropical cyclones every year. But overall, the spatial distribution looks reasonable, and we will see a westward, propagations in the deep tropics and the eastward in the deep tropics and westward in the mid latitudes. And also, the intensity looks kind of not too bad. For the 25 kilometer model, we can at most reach to the category 4 storm, which is roughly 65 to 70 meters per second, which is not as strong as what we observed in the real natures. But considering the resolution deficit, I think this is still quite reasonable. But there are still some biases exist, especially over in the North Atlantic basins, where we find that the actual TCC number seems to be towards the lower bias, roughly half of what we observed. And also the location of the TC seems to be way towards the higher latitudes. This is some biases exist in the fully coupled simulations. But given that our mesoclip data sets provide a very unique theme ensemble of the different future climates, so we want to know if we can using our data set to try to quantify the tropical cyclones' impact or the risks that are exposed to the human community. So talking about the risk assessment, it is actually quite different, not quite, but slightly different from the typical tropical cyclone dynamic studies. In the tropical cyclone dynamic study, people may focus more on the maximum tropical cyclone intensity. But if we talk about the risks that tropical cyclones can expose to the human community, we need to considering the tropical cyclone spatial expansion. In other words, we have to consider where that the location in the human live can be impacted by the tropical cyclone's winds. This is not just a single maximum intensity value problem, but actually a two-dimensional spatial expansion problem. So in order to test whether our data sets can be used for the tropical cyclone risk analysis, we also need to verify our tropical cyclone structure and also its spatial distribution too. So here shows the composite of the two-dimensional surface winds from the satellite reconstructions at the top and the high-resolution simulation at the bottom. So the left column figure is a composite made just before the hurricane makes landfall, while the right column figure shows the result just after the tropical cyclone made landfall. And this different color indicates the tropical cyclone surface wind speed. You can find that although the maximum tropical cyclone's intensity seems to be underestimated, but in terms of the spatial expansion, it is actually pretty good represented in the 25 kilometer model. So the gear force wind is roughly 17.5 meters per second. The wind radii is roughly 300 kilometers to 400 kilometers in our high resolution simulation, which is consistent with observations. And within the eye walls, we do see a strong very intense tropical cyclones winds can be as strong as 50 meters per second, which is consistent with the satellite observations. After hurricane made landfall, due to the surface frictions and also the deficit in the enthalpy fluxes, so the tropical cyclone intensity gets rapidly decayed, and our model is also capable to represent these processes. And talk about tropical cyclones induced risk, we also need to consider the rainfall, right? So because sometimes it's really the flooding events cause the biggest damage to our house properties. We want to quantify if our simulation can reasonably capture the hurricane-induced extreme precipitations. So to do that, let's focus back to the CONUS, where we have the most advanced observation network. And here, the panel A shows the hurricane-induced annual maximum rainfall and over the CONUS region using the NOAA observation network. So as we expected, the tropical cyclones indeed bring lots of the rain in the coastal areas, which is showing in this blue contour. You will see over the Gulf Coast, over the east coast of US, we do see several of the red spots. And a little bit surprising to me that when we look at tropical storm airing, which is in terms of the intensity metrics, it's very weak, but it indeed produced some strong rainfall events in the mid of the US, which is never considered as a tropical cyclone prone region before. But when we look at tropical cyclones report in the 2007, these areas, the remnant system of the ravine actually interacted with some frontal system and caused flooding events in the Oklahomas and Midwest of the US, which is quite exceptional. So in order to compare our simulation with true observations, because our simulation has a Tema ensemble, which brings much more data sets compared to observation. So the evaluation is made based on the statistical perspectives. So I computed the 25th percentile, 75th percentile, and also median values to want to make sure our interquartile range can reasonably cover this observed value. So the result is, again, still pretty promising and very encouraging. We do find that roughly the median values can represent this observation pretty well. And of course, the observation is still within this interquartile range. This result suggests that with our Tema ensemble simulation, we can indeed make some risk analysis about tropical cyclones. So here I try to quantify the tropical cyclones induced compound wind and precipitation hazards. The definition of this compound hazard is that the tropical cyclones induced the wind and precipitations, both of them are stronger than the corresponding the wind and the rainfall very high extreme value or the local threshold. And this exists, and this threshold is unconditioned on the tropical cyclone frequencies. It's unconditioned on tropical cyclone occurred or not. In other words, so we define a compound hazard events for those locations that the tropical cyclones induced wind and rainfall hit this local extreme value. And we count that event as one compound hazard. All right, so after that, we can try to compute the probabilities of this compound hazard with these equations and try to estimate the joint return period to try to quantify these risks. And the left column figure is actually showing the true observations, and the right column figure shows our simulations. With a different color indicates a different joint return period, which stands for the averaged interval of this joint compound hazard events occur. So again, consistent with our experiences, the global coast area seems to be the hurricane-prone region, right? Including the Gulf Coast and Southeast China, and also the India, and also parts of the Mozambique Channel. So these results looks pretty nice simulated by the models, but again, for the US side, the model seems to be a little bit underestimated. So here, look at the future changes under RCP 6.0 scenario. The panel A shows tropical cyclone frequency changes from the 1920 to the 2100, with a thin red color indicates the different ensemble member, and this thick red color indicates ensemble average. The blue and the green shows the observation and the real analysis too. So probably a little bit contradictory to what we expected before. With the warming of the climate, actually we do see a decrease of the tropical cyclone frequencies. But this may not be the most important information. Looking at the spatial distribution, we find that the tropical cyclones track tends to be moved more towards the higher latitudes, where we find a positive anomaly of tropical cyclones track densities, while the negative anomalies in the deep tropics, positive anomaly in the higher latitudes, but negative anomaly in the deep tropics. And this is especially quite outstanding in the Pacific sector. You'll see that there are more and more tropical cyclones to occur over the East China, over the Japan, and even in the New Zealand. And same as in the US side, we do see the decrease of the TC's occurrence in the Caribbean seas, but overall increasing of tropical cyclone occurrence in the Gulf Coast as well as in the east coast of the US. And in terms of the joint return period computations, we find that the value seems to be decreased. The decreased joint return period means that the average interval of the compound hazard will be more frequent. In other words, the tropical cyclones induced compound hazard will be more frequent, which is obviously bad news. And the panel D is trying to make the fractional changes, compute the fractional changes of joint return period, and I also make the global average as a function of the distance to that length. The overall take-home message is that although the tropical cyclone's frequencies seems to be decreased, but the tropical cyclone-induced compound hazard will be increased. Probably more strikingly, the increase within the near coast region is roughly 100%, but for those intermediate inland regions, which is in between 100 kilometer to 500 kilometer, seems to be increased, which this means that the tropicals, the intermediate inland region, which historically not seen as the tropical cyclone prone regions, will be very likely be more frequent exposed to tropical cyclones induced compound hazard. So this is another quick summary. So I'm not going to repeat it, and because time is limited, I will move on to my final section. So far, I've been talking about how to use Mesoclip data sets to improve our physical understanding and climate risk assessment. So for the last part of my talk, I want to slightly shift my gear and try to introduce some additional potential usage of Mesoclip data sets, which is about AI machine learning. So for the AI experts, we all know that some of maybe very prevailing AI-based numerical weather prediction system, they are primarily trained based on the EI5 data sets. Although EI5 data sets is a very fundamental or very important data set for all types of analysis, but it only consists of roughly 80 years of the historical weather events and also only single realizations of the climate, which is what we observed. So it is still not quite sure or puzzling that this EI5-based training is really capable to predict those unprecedented extreme weather events that have not been observed before. So this is especially concerning because this EI5 only provides us some limited sample of the extreme events, and we are all care about the future extreme events, right? So if it cannot cover the full spectrum, can the AI model do the reasonably good job? We still don't know that. However, the Mesoclip data sets provides slightly different situations. So over the years, we have accumulated more than 7 petabytes of the higher resolution simulations, which represents more than 8,000 years of the runs and spanning the big spectrum of the climate with different climate forcing, climate scenario, and even some sensitivity simulations. So this data set provides us a very rich data and includes thousands or even millions of tropical cyclones and other extreme events. So this naturally raises a question that if we can use Mesoclip data sets as a new data source for the AI and for the climate and weather AI applications. And I think the overall answer is yes. And I want to firstly convince you from a very simple and easy application that focusing on the tropical cyclone. So before the AI becomes populated, the human intelligence already find that The tropical cyclones tends to occur in some certain favorable locations. These certain environmental conditions include the warm seasonal temperature, the unstable atmosphere, include the deep layer of moist air, and also moderate to the weak vertical wind shear. So in 2004, the Emmanuel and Nolan proposed a very pioneering research framework called GPI, Genesis Potential Index, which tried to summarize these favorable conditions into a mathematically consistent way and give rise a very clean and beautiful math equations. Here, the GPI stands for the environmental favorability of tropical cyclone genesis. With bigger the value, it stands for tropical cyclones are more likely to occur. So the different variables indicate different physical variables like the vertical wind shear in the V shear and the tropical cyclone potential intensity in the V part, and relative humidity and vorticity here. So this GPI was originally designed only for the North Atlantic and using a climatological value, but it turns out that it can do a pretty good job in to understand the inter-annual variability in the North Atlantic. But comes to the Western Pacific, this tells us a very different story. The correlation coefficient is still pretty strong in terms of the seasonal cycle, but the correlation is very weak, almost zero in terms of the inter-annual variability. So this actually motivates me to think about if we can use the machine learning method to try to understand this nonlinear empirical relationship between the large-scale environmental favorability of tropical cyclone genesis and the tropical cyclones activity. So this actually leads me to publish my paper in 2003 and using the convolutional neural network. And of course, based on today's standards, this CNN, convolutional neural network, is kind of toy model. But it turns out that it's still very useful, can lead to some breakthrough in our physical understanding too. So this is a very simple framework. So what I input to the AI model is actually a two-dimensional map of the different variables, physical variables, including vertical wind shear, SST, and column saturation deficit, and relative humidities, as well as relative vorticities. And the predictant is actually the seasonal tropical cyclone activity, includes the number of tropical cyclones, hurricanes, and the cumulative cyclone energy. And here shows some validations about my AI framework. So the black color shows what actually observed in the nature, and this blue color shows the AI emulation results. You can see that the correlations can be as high as 0.98, and RMSE is also pretty minimum comparing to its climatological value. Same as the cumulative cyclone energy, which is another physical quantity to try to summarize the seasonal scale tropical cyclones total energy from the total kinematic energy. So you will see that the correlation is 0.93 and RMSE is still roughly 1/10 of the climatological mean value. So after we have this AI framework, we can make some lots of the application. So one important data-related application is to try to predict tropical cyclones activities a season ahead, which is known as a seasonal tropical cyclone prediction. So here shows some evaluation of the actual prediction scale. Since we are interested in tropical cyclones occurred during the June to November, we can initialize our prediction system either in the January, February, or all the way to the June 1st. This is a different lead time. And this box plot actually summarizes the prediction scales in terms of the ACC, anomaly correlation coefficient. And this horizontal line indicates the value of the persistent predictions, and which provides us a bottom bar to define a scale for prediction. This means that as long as this hybrid AI-driven predictions can be higher than this horizontal persistent prediction value, your new prediction is more valuable. So here we find that for the North Atlantic, we can achieve a scale for predictions as early as in the February, and the higher prediction scales can reach to roughly 0.65 when the prediction initiated in the May 1st. And this is actually very encouraging, and which means that using the AI, we can try to provide a scale for prediction with a full month lead time so that it can leads to some long-term decision and make sure these stakeholders and decision maker can well prepare for this incoming tropical cyclone season. Another applications is to reconstruct historical TC records. So the raw TC observations in the North Atlantic can be traced back to 1851. And however, as you can imagine that this results may not be quite reliable that before the satellite era. So think about sometimes in the 18th century, right? So where the global trade system is not as populated as these days, and also this global ship route is not as dense as so far. Although some ship log may be monitor the tropical cyclone currents, but it may also miss tons of the storms that never been seen by this ship or by this cargo crew. So that this can be potentially leads to some biased assessment of tropical cyclones trend, and this actually motivates me to think about to reconstruct the historical tropical cyclones records that using my CN framework together with some low resolution 20th century reanalysis. And the results are shown here. This reconstruction is showing in this blue color and this black color showing the raw observations, and this green color shows some statistical based bias corrections proposed by the Vicky and Knudsen. And it's very interesting to find that these evaluations in these overlapped regions is still pretty robust. The correlation coefficient 0.66 again suggests that my CN framework indeed is quite useful and reasonable. Again, from this map, we find that if we only look at the black curve, we can maybe conclude that tropical cyclones in the North Atlantic seems to be increased a lot in the historical 150 years. However, if we consider in these reconstructions that potentially fill the missed tropical cyclone records, we find that there is no significant trends at all. On the other hand, we do see some multi-decadal variability. So although we are still very active to understand what drives this multi-decadal variability, but one important take-home message, at least from this map, is that for the recent 4 decades, the 40 years from the 1980, we do see an upward trend in the North Atlantic, but this upward trend may not necessarily be a true climate change-induced upward trend, but more likely it is a part of the multi-decadal variability. So using the TCCN, we can reasonably reconstruct the historical tropical cyclones records. Also, now let's really focus on something more contemporary and something new in the AI field. So through this, this visit, I'm actually building a new collaborations with the CISL's Miles team, which we want to try to build a purely data-driven, fully coupled Earth system emulator. So here shows a schematic plot of our AI design. I just copied this from the drawing. And this is a very complicated AI architecture, but it doesn't matter. So the underlying logic is pretty simple. What we want to do is actually try to build a sophisticated state-of-the-art architecture to try to learn the nonlinear relationship between the CSM state at time equal to t and CM state at time equals to t plus 6 hours. Using this AI emulator, we try to build this connection. So once we finish our training and also build a very robust framework, we can then apply this emulator to a new initial state and then trying to predict the CSM state as the next 6 hours. So we then use the next 6 hours to drive another emulations to predict the state for the t plus 12 hours. And we can do it iteratively, autoregressively, which can eventually lead to a long time of the emulation, which is pretty much similar to what CSMHR is doing. So here shows some preliminary results. Yes, so this work is actually done by my student, Yan Chen. Unfortunately, he's not here today, but I want to give all the credits to him. So this is again, movie from the emulation that I explained earlier. And this is based on the roughly 1 week of the training. And you will see that this result is quite good, and in the AI standard. So we do see that the left column figure shows the animation of the bottom U wind, and the right column figure shows the precipitation emulation. So we do see that the emulators can actually capture this mid-latitude frontal system. You will see this frontal rainfall that propagate from the east to the west. And more than that, the model can even capture some mesoscale features in the deep tropics. And sometimes it can even generate tropical cyclones, which is very fascinating. And another very big win for this AI side is it's computationally very cheap. So after 1 week of trainings, here shows some benchmark of these emulations. So using just single 1 GPUs on the direct chills, we can achieve roughly 6.6 simulation per year. We can achieve roughly 6.6 simulated years per work clock date. And this is just single 1 GPU. We can easily linearly scaling up to roughly 60 plus year per days with, for example, 10 GPUs. And this can be maybe applied to our different CSM simulations, which can be further used to expand our MesoClip data ensemble size. So here shows the summary of my final sections. Essentially, we find that the MesoClip datasets provides a very unique opportunity for the AI machine learning applications. It provides us more than 7 petabytes of datasets and thousands of simulation years, which contains a big spectrum of the climate extreme events and also the climate different scenarios. And we want to leverage the datasets to advance our AI applications. So the results I'm showing here was simply atmosphere-only emulators, and I want to see that the ocean only, the land only, and the fully coupled emulation training is still undergoing. So hopefully I can provide you some more results soon. So with that, I think I can stop here and happy to take any questions.
You mentioned the emulators. Oh, sorry. Yeah. With the emulator, did you say, so this was trained on one member?
This is, based on one member on simulation.
Yeah, so the speed is great. I'm curious if using the one member, you can capture the variance seen in the ensemble members. Have you looked at that yet?
Not yet. So because of some technical difficulties, we just, restore our HPC access yesterday. So I just made this animation today. So we haven't really looked at these results yet. But again, so based on our training, we find this can be something we can test it. As you said, if we can use the one member ensemble to represent the full ensemble size. So I think this is a very exciting work.
Yeah, cool. Thank you.
Hi, thank you for the presentation. It was really interesting. Regarding the frequency of TCs,
your model or MesoClip produces more than is observed, and particularly that's true in the Southern Hemisphere.
Yes.
Do you have any ideas for why that might be in terms of differences in the large-scale flow or other factors that contribute to TC genesis?
Great question. So I've been discussing this with Julio Bacaminsta before, and we hypothesized that this is because the SBCZ is maybe too active in the CAM simulation here. So in the SBCZ in our simulation is too unstable. You will see there are lots of meandering, like the mesoscale features, the shredding from the SBCZ. And the shredded tropical vortex, eventually, further grows to the tropical cyclones. So this probably is the one reason why we see too many tropical cyclones in the southern hemisphere.
Great, thank you.
Sure.
Thinking mainly about the first part of your talk, and you were looking at MCSs and tropical cyclones and extremes of precipitation. Do you have a sense, I know you haven't got the simulations, but do you have a sense of the relative importance of the higher resolution ocean in any of that finding? Or do you think it's all coming from the atmosphere?
Great point. So this is something we are working on right now. So we have a new set of simulation that force atmosphere-only simulation with a low resolution SST. So comparing to the higher resolution SIC forcing, we want to have more knowledge on that. But I think according to some new publications, which demonstrates the importance of the temperature gradient in inducing the sensible heat flux, and which may eventually fuel the mesoscale convex system. So I really think that the mesoscale ocean eddies can do a similar thing, which means that a higher resolution ocean may give rise to some strong MCSs or convex system of the global ocean. But the convection over the land area is slightly different. So we do think that it is really due to the higher resolution atmosphere model leads to the better convections over the land area. Yeah, Clara.
Yeah, I had a related question. You didn't show MCS results over the ocean. I think that would be very interesting, and if it
Exactly, yes.
Yeah, is that because we don't have the observations to compare to, or yeah, these were all beautiful, but they're just land.
Yeah, I do have the results on my own, but I think the paper of this is actually trying to emphasize the rainfall over the land alone.
Yeah.
But yeah, we do see tons of the MCSs over the ocean too. So yes, this is definitely something we will look at later. Yeah. Hi, Fred. Yeah.
Yeah, just a comment. Like, if you go to the figure where you show the frequency of, yeah, oh no, this one is. Oh, I thought this one was. Sorry. But yeah, we do have this one as a global map also, not just the land.
Saw it in your animation at the beginning.
Yeah, that's a good point. Yeah. So in this animation, this purple color actually centers the MCSs. You'll see lots of the MCS shredding from the ITCZs and also SPCZs. And yeah.
Don't have anything online right now.
We have about 2 minutes left.
Any last minute questions in the room? Okay, I think we can wrap up.
All right. Want to thank Dan again for spending part of his summer here with us at NCAR.
Thank you. Yeah.